Hello there and welcome to Physics with William, where we explore the fascinating and sometimes bewildering world of science. Here, we take things slow and steady, peeling back the layers of complex ideas and finding beauty in how the universe works. Tonight, we embark on a journey through a discovery that has stirred the scientific community like few others, a discovery that challenges what we thought we knew about physics and magnetism. What if I told you that what we thought was impossible, something that was purely theoretical, might have just been found? What if, after years of searching, scientists at CERN, home to some of the most mind-bending experiments on Earth, discovered something that could redefine how we understand the universe at its most fundamental level? Today, we're diving deep into the magnetic monopole, an elusive particle that has been theorized for nearly a century and, according to some recent findings, might just exist after all. But before we dive into the specifics, I want you to think about something. Have you ever thought about the impossible? We all have moments when something seems out of reach, too far to touch, and yet we keep pushing forward, trying to make the impossible real. Have you ever wondered what it would be like to discover something that defies all known laws, a discovery that changes everything? Take a moment, think about where you are right now, what time is it where you are, and let's see if we can make sense of this new chapter in physics together. If you find this soothing, intriguing, or even a little mind-boggling, a like, a subscribe, or just a share would mean a lot. It helps bring this corner of science to others who might need a little calm in their curiosity. But let's not waste any more time, let's get into it. The magnetic monopole, a concept that defies everything we know about magnetism, has been a long-standing curiosity in the scientific community. For as long as we've studied magnets, we've understood one core principle. Magnets have two poles. There is a north pole and a south pole. And no matter how many times you break a magnet into smaller and smaller pieces, it always has both a north and a south pole. This is an axiom of magnetism. There's no such thing as a single magnetic pole, or at least, that's what we've been told for centuries. But in the world of physics, the boundaries between the possible and the impossible are often thinner than we might think. As much as science prides itself on being grounded in established facts, there are times when the impossible becomes possible. The magnetic monopole is one of those concepts, an idea that has always existed in the world of theoretical physics, but never in the realm of reality. Until recently, that is. The idea of a magnetic monopole goes all the way back to the early 20th century. In 1931, the renowned physicist Paul Dirac introduced the possibility of a particle with only one magnetic pole, an idea that was purely theoretical at the time. He suggested that such particles could help explain some strange aspects of quantum mechanics, and might even be linked to the very fabric of the universe itself. However, despite decades of research and countless attempts to find them, magnetic monopoles remained elusive, like an idea just out of reach, a mirage in the world of physics. But here's the thing. Just because something hasn't been found doesn't mean it doesn't exist. Science has a way of catching up with what we once thought was impossible, and that's where CERN, the European Organisation for Nuclear Research, comes into play. CERN is already known for its groundbreaking research, most famously for its work with the Large Hadron Collider, where scientists discovered the Higgs boson, an achievement that was once thought to be a pipe dream. Now, CERN might have just made another impossible discovery. According to recent reports, scientists at CERN have found evidence that could suggest the existence of the magnetic monopole. It's easy to get lost in the details of such a discovery, but let's step back for a moment and appreciate what this means. For decades, scientists have been trying to detect these particles to prove that they exist in reality. Yet time and time again, experiments have come up short. And yet, in the world of science, even failures can lead to breakthroughs. Every failed experiment offers a new piece of the puzzle, a clue that takes us one step closer to understanding the universe. So, how did CERN, one of the most advanced scientific institutions in the world, end up on the verge of making a discovery so monumental? The answer lies in the nature of the experiment itself. To detect a magnetic monopole, you need to be looking for something completely different. You can't just use a standard magnetometer, the tool used to detect regular magnetic fields. A monopole, if it exists, behaves very differently from what we know about magnets. While a traditional magnet has both a north and a south pole, a monopole would have only one. Think about it. If you held a monopole in your hand, it would be like holding just one side of a magnet. It would have a north pole without a corresponding south pole, a concept that sounds impossible when you consider how magnets behave in our everyday world. This is where the beauty of experimentation comes in. At CERN, scientists have been working with extremely high-energy particle collisions, and in these collisions they've been searching for new particles that might emerge, particles that have never been observed before. And in this search, there's a theory that has guided them, the idea that monopoles might appear in certain conditions, such as when particles are moving at extremely high speeds. The conditions that could create these exotic particles are rare, but they might just be possible in the right environment, and CERN's advanced facilities give scientists the tools to recreate those conditions. The discovery, if confirmed, will not only mark a significant moment in physics but will open up new questions. If the magnetic monopole exists, what does that mean for the laws of electromagnetism? How do monopoles fit into the theory of quantum mechanics, a framework that has already had to adjust to many strange and unexpected phenomena? And more importantly, what could this discovery mean for the future of particle physics and our understanding of the universe? As we stand on the precipice of this potential discovery, it's important to realize that this is not just a scientific breakthrough, it's a glimpse into the unknown. It's a reminder that in science, the impossible is often just a question we haven't yet answered. So, as we continue to unravel the mysteries of the magnetic monopole, let's keep our minds open, knowing that we might be witnessing the birth of a new chapter in our understanding of the universe. Now, as we prepare to dive deeper into this discovery, let's consider what magnetic monopoles could mean for us, and how their existence could change everything we thought we knew about the forces that shape the very fabric of space and time. But before we do, think about this. What if the search for the impossible is really just the search for something we already know exists, waiting to be discovered? Let's take this journey one step at a time. The quest for the impossible has always been a defining feature of human curiosity. From the earliest days of recorded history, people have gazed up at the stars, wondering about the vastness of the universe and what lies beyond our understanding. It is in this space of wonder and imagination that science begins, when the known world is stretched by the edges of the unknown. Scientists, driven by an insatiable curiosity, have long sought answers to questions that seem too big to be answered. The story of the magnetic monopole is a perfect example of this. For nearly a century, scientists have been chasing the idea of a particle that defies the very rules of magnetism, a particle that should not exist according to our current understanding of the world. Yet the search for the magnetic monopole continues, driven by the belief that even the impossible might one day be discovered. The journey began long before we even knew what we were looking for. In the early 20th century, a new idea began to take shape in the minds of physicists, an idea that would later ignite one of the most persistent and challenging quests in the history of science. Paul Dirac, a brilliant theoretical physicist, was the first to propose the possibility of a magnetic monopole in 1931. In his groundbreaking work, Dirac realized that the equations of electromagnetism, which had been developed by James Clerk Maxwell in the 19th century, could be modified in a way that allowed for the existence of a particle with a single magnetic pole. This was a bold idea, as it directly contradicted what had been accepted in the world of magnetism for centuries. According to conventional wisdom, magnets always had two poles, north and south, and no matter how many times you cut a magnet in half, you would always end up with two poles. The concept of a magnetic monopole, a particle with only one magnetic pole, seemed like an impossibility. But Dirac's reasoning was sound, and his work sparked a revolution in theoretical physics. He showed that the existence of a monopole would help explain certain aspects of quantum mechanics, and that it could even be tied to the fundamental structure of the universe itself. Dirac's ideas opened the door to new possibilities, suggesting that the universe might be far stranger than we had imagined. His predictions were not just theoretical musings, they were grounded in the very equations that governed the forces of nature. Yet, despite the elegant logic of Dirac's theory, no experimental evidence for the existence of monopoles was found for many years. The quest for the impossible had begun, but the journey would prove to be long and filled with obstacles. As the decades passed, the search for magnetic monopoles became a central theme in the field of particle physics. In the 1970s, the advent of high-energy particle accelerators and more advanced experimental techniques brought new hope. Physicists began to look for monopoles in particle collisions, believing that if they existed, they might be produced in the high-energy environments created in these experiments. Despite countless experiments, however, no monopoles were found. The absence of evidence led many to believe that Dirac's prediction was simply a fantasy, a brilliant but ultimately incorrect idea. The lack of results seemed to reinforce the belief that monopoles could never exist, and the search for them began to fade into the background of particle physics. However, the story of the magnetic monopole would not be so easily forgotten. The idea remained embedded in the minds of many scientists, and the possibility of discovering such a particle continued to inspire new generations of researchers. By the late 20th century, the quest for the magnetic monopole had become a symbol of the limits of human knowledge. It was a challenge that seemed insurmountable, a mystery that lay just out of reach. The idea of discovering the impossible had become a kind of holy grail for physicists, a pursuit that represented the very essence of scientific inquiry. The belief that there is always something more to discover, even when the odds seem impossible. In the world of physics, the impossible is often just a stepping stone to the next great breakthrough. For decades, the search for the magnetic monopole was viewed as a fruitless endeavour, but the scientific community refused to give up on it. And it wasn't just the physicists who were interested. The public had become fascinated by the idea of a particle that could break the rules of magnetism. The story of the monopole had become a part of the cultural imagination, an example of the kind of scientific mystery that sparks curiosity and wonder. It represented the intersection of theoretical physics and the unknown, a place where logic, imagination, and ambition collide. It wasn't until the 21st century, when the power of particle accelerators like the Large Hadron Collider at CERN came into play, that the search for the monopole took on a new urgency. CERN, already known for its work on the Higgs boson, became the focal point for a new generation of physicists determined to prove or disprove the existence of magnetic monopoles. Using the latest in experimental technology, scientists began to push the boundaries of what was possible. Their goal was simple, yet profound: to find evidence for a particle that had eluded detection for nearly a century. But this search would not be an easy one. Even with the immense power of the Large Hadron Collider, finding a monopole would require overcoming numerous challenges. The conditions needed to create a monopole in the lab were extraordinarily rare, and detecting one was even more difficult. But as with all great scientific quests, it was the challenge itself that made the pursuit so compelling. The magnetic monopole represented the idea that even the most difficult problems could one day be solved. It was a reminder that in science, the impossible is only a temporary barrier. It is the relentless pursuit of knowledge, the refusal to accept the limitations of what we know, that drives discovery. The quest for the magnetic monopole, though long and filled with setbacks, is a testament to the human spirit of inquiry. An unyielding belief that there is always something new to learn, no matter how improbable it may seem. As we look back on this journey, it becomes clear that the search for the magnetic monopole is not just about finding a particle. It is about challenging our understanding of the universe and pushing the boundaries of what is possible. In the years since Dirac first proposed the idea of a monopole, the pursuit has inspired generations of scientists to think differently, to question the established laws of physics, and to imagine a world where the impossible becomes possible. And while the discovery of the magnetic monopole may still be on the horizon, the journey itself has already made a lasting impact on our understanding of the universe. The quest for the impossible, as embodied in the search for the magnetic monopole, is far from over. It is a journey that continues to shape the future of physics, a journey that will likely yield new insights into the very fabric of reality. And for those of us who follow this path of discovery, there is no telling where it might lead. Perhaps the impossible will one day be found, not as a singular particle, but as a new way of seeing the universe. For now, we continue the search, knowing that in the world of science, even the most elusive dreams may one day become a reality. A magnetic monopole, if it exists, is a particle that could forever alter our understanding of magnetism and the forces of nature. For centuries we've known that magnets always have two poles, a north and a south. This principle is so deeply ingrained in our understanding of magnetism that it seems almost impossible to imagine anything different. But a magnetic monopole, by definition, would be a particle that has only one magnetic pole, either just a north or just a south pole, with no counterpart to balance it out. This seemingly simple change challenges everything we know about magnets, electromagnetism, and the very nature of magnetic fields. To understand what a magnetic monopole is, it's important to start with the basics of magnetism as we know it. In a traditional magnet, the magnetic field is generated by the motion of charged particles, primarily electrons. These magnetic fields radiate out from the north pole of a magnet and return to the south pole, forming a closed loop. If you were to cut a magnet in half, you wouldn't end up with a single pole. Instead, you'd get two new magnets, each with both a north and south pole. This phenomenon, where every magnet has two poles, has been known since the time of the ancient Greeks. It's so fundamental to our understanding of magnetism that we rarely question it. Yet, the idea of the magnetic monopole forces us to ask, what if there were a particle with only one pole? The concept of the magnetic monopole is not entirely new. It first emerged in the early 20th century, when the physicist Paul Dirac proposed that the existence of such particles might help explain some of the mysteries of electromagnetism. According to Dirac's theory, the magnetic monopole would be a particle with a single magnetic pole, much like an electric charge, which can exist as a positive or negative charge. This idea was revolutionary, as it suggested that magnetism, like electricity, might have a more fundamental structure than we previously thought. However, even Dirac, one of the giants of theoretical physics, could not predict whether these particles actually existed in nature. They remained purely theoretical for many decades. In Dirac's view, the existence of magnetic monopoles could help explain the quantization of electric charge. The idea was that if a magnetic monopole existed, it would force the electric charge to be quantized in discrete amounts, just as the electric charge of an electron is fixed. This idea could resolve a number of inconsistencies in the way we understand the fundamental forces of nature, particularly in the relationship between electric charges and magnetic fields. The problem, however, was that no one could find any experimental evidence of these elusive particles. Every experiment conducted to search for magnetic monopoles came up empty, and for many years it seemed as though they were nothing more than a theoretical curiosity. But just because something can't be detected doesn't mean it doesn't exist. The idea of the magnetic monopole continued to intrigue physicists, and in the decades that followed, scientists developed new theories and methods to search for these elusive particles. The theoretical possibility of a magnetic monopole was an exciting challenge, but finding it in the real world proved to be another matter entirely. Despite the failure of earlier experiments, the search continued, and the quest for the magnetic monopole became a defining pursuit in the field of particle physics. The key to understanding the magnetic monopole lies in the laws of electromagnetism, particularly Maxwell's equations. These equations describe how electric and magnetic fields interact, and they form the foundation of classical electrodynamics. However, in the version of Maxwell's equations that we use today, there is no place for a magnetic monopole. These equations are symmetrical when it comes to electric charges, meaning that for every positive charge there is a corresponding negative charge. But when it comes to magnetic fields, Maxwell's equations only account for dipoles or pairs of magnetic poles. There is no provision for a single magnetic pole, a monopole, in these equations. This means that in our current understanding of electromagnetism, a magnetic monopole simply can't exist. Yet, the possibility of such a particle has remained a tantalizing idea for physicists. To visualize a magnetic monopole, imagine a magnet, but instead of having two poles, it only has one, either a north or a south. If you held such a particle in your hand, the magnetic field would emanate from the single pole, much as it would from the north or south pole of a conventional magnet. However, unlike ordinary magnets, a magnetic monopole would not have a corresponding opposite pole. This would change the way we understand magnetic fields, and could lead to new insights into how these fields behave at the most fundamental level. In practical terms, discovering a magnetic monopole would have profound implications for many areas of physics. It would provide new insights into the behavior of magnetic fields, and could even help resolve some of the most perplexing problems in theoretical physics. For example, the existence of a magnetic monopole could lead to a deeper understanding of the connection between electromagnetism and the other fundamental forces of nature, including gravity and the weak and strong nuclear forces. This could bring us closer to the long-sought goal of a unified theory of everything, an overarching framework that explains all the fundamental forces in the universe. Furthermore, the discovery of a magnetic monopole could have practical applications beyond the realm of theoretical physics. If monopoles could be created or controlled, they could potentially revolutionize our understanding of materials and their magnetic properties. Scientists have long been interested in creating new materials with exotic magnetic properties, and the magnetic monopole could provide the key to unlocking new technologies, from advanced electronics to more efficient energy storage systems. Yet, despite the potential benefits, the discovery of the magnetic monopole has proven to be elusive. The particles are extraordinarily difficult to detect, and the conditions required to produce them in the lab are extremely rare. The search for magnetic monopoles has led scientists to develop new experimental techniques, from high-energy particle collisions to advanced detectors designed to identify the faintest signals of these particles. But until recently, the evidence for their existence has been inconclusive. This brings us to the present day, where the search for magnetic monopoles has entered a new phase. Theoretical models have predicted that monopoles could be created in the high-energy environments of particle accelerators, such as those at CERN. These models suggest that if the right conditions are met, magnetic monopoles could emerge in particle collisions, just as other exotic particles like the Higgs boson were created and detected in experiments. But even with the power of the world's most advanced particle accelerator, finding a magnetic monopole is still an immense challenge. As we continue to probe deeper into the nature of the universe, the question remains, what exactly is a magnetic monopole? Is it the missing piece of the puzzle that could lead us to a deeper understanding of the forces that govern the universe? Or is it merely a theoretical concept that will forever remain out of reach? The answer, we hope, lies somewhere in the future, as scientists at CERN and around the world continue to search for the elusive particle that could redefine our understanding of the universe. The magnetic monopole remains one of the great mysteries of modern physics, and perhaps one day, the impossible will finally become real. Until then, the search continues, with the possibility of discovery just on the horizon. The search for the magnetic monopole is a journey that stretches across the landscape of scientific history, a quest that has spanned decades and traversed the boundaries of imagination, theory, and experimentation. It is a search that began with a bold and groundbreaking idea and has evolved into one of the most enduring and elusive pursuits in the field of particle physics. The magnetic monopole, a particle that was once deemed impossible, has remained just beyond the reach of experimental detection, despite the tireless efforts of countless scientists over the years. Yet, the pursuit of this impossible particle has led to some of the most profound advancements in physics, deepening our understanding of electromagnetism, quantum mechanics, and the very nature of the universe. The journey toward discovering the magnetic monopole began with the theoretical work of Paul Dirac in 1931. Dirac, a British physicist known for his work in quantum mechanics, was the first to seriously propose the idea of the magnetic monopole. His insight was revolutionary. He recognized that the equations governing electromagnetism could be modified to allow for the existence of a particle with a single magnetic pole. At the time, it seemed like an impossible idea. After all, every magnet that had ever been observed had two poles, north and south. The idea of a single pole, a magnetic monopole, appeared to defy the fundamental laws of magnetism as understood at the time. But Dirac's theoretical work was not just a flight of fancy. It was grounded in the math that underpins much of modern physics. His equations suggested that magnetic monopoles could exist in nature, and that their discovery could help explain some of the mysteries of the universe. For example, Dirac believed that the existence of monopoles might help explain the quantization of electric charge, a phenomenon that had puzzled physicists for years. If monopoles existed, they would have to be linked to electric charges in a way that would enforce the quantization of charge, meaning that electric charge could only come in discrete units, just as the electric charge of an electron is fixed. This was a tantalizing possibility, and it gave physicists a reason to believe that monopoles might not just be a theoretical curiosity, but a real, observable particle that could help solve some of the most fundamental problems in physics. Despite Dirac's groundbreaking work, the search for magnetic monopoles would prove to be far more difficult than anyone had anticipated. In the years following Dirac's proposal, physicists attempted to detect monopoles in a variety of ways, but every attempt to directly observe a magnetic monopole failed. The search for monopoles became a central focus of experimental particle physics, but the elusive nature of the particles meant that they remained just out of reach. The idea of the monopole became a kind of holy grail for particle physicists, a goal that seemed perpetually just beyond the horizon. As the decades passed, scientists refined their understanding of electromagnetism and the forces that govern the universe. New theories emerged and experimental techniques advanced, yet the magnetic monopole remained undetected. One of the challenges in finding a monopole is that it behaves very differently from the common magnets we encounter in everyday life. Traditional magnets have both a north and a south pole, and their magnetic fields form closed loops. A magnetic monopole, on the other hand, would have a single magnetic pole, and its magnetic field would not be like the familiar dipole field of a regular magnet. This means that detecting a monopole would require an entirely different kind of experiment, one that could isolate the behavior of a single pole in a way that had never been done before. By the 1970s, high-energy particle accelerators had become a key tool in the search for exotic particles like the magnetic monopole. These accelerators, such as those used at CERN, could create the kinds of high-energy collisions needed to potentially produce monopoles. The idea was that under the right conditions, when particles collided with enough energy, they might produce a monopole, which could then be detected by the sophisticated instruments used in these experiments. But despite the immense power of particle accelerators, no monopoles were found in these experiments. The elusive particle remained just out of reach, as though it were hiding in the vastness of the universe, waiting to be discovered. The 1980s and 1990s saw further attempts to detect magnetic monopoles, using new technologies and innovative methods. Researchers began to look for monopoles in more subtle ways, seeking out any possible clues that might indicate their presence. Some experiments focused on detecting the presence of monopoles in cosmic rays, high-energy particles that are constantly bombarding the Earth from space. Others turned their attention to materials that might be able to trap and contain monopoles, searching for any signs that these particles might be interacting with matter in unusual ways. Yet despite these new approaches, the search still came up empty. the magnetic monopole remained one of the great unsolved mysteries of physics. As the search for the monopole continued, it became clear that finding such a particle would require more than just technological advances. It would require a shift in how scientists approach the problem. The theoretical understanding of monopoles evolved, as did the experimental methods used to detect them. One of the key insights that emerged in the 2000s was the possibility that monopoles might not be point-like particles at all, but rather emergent phenomena arising from more complex systems. Some theorists suggested that monopoles could appear as collective excitations in certain materials, much like how the behavior of many particles can give rise to phenomena like superconductivity or magnetism. This new understanding opened up new avenues of research, and once again, the search for the magnetic monopole was revived. In the 2000s, new experimental techniques were developed that allowed for more precise measurements of the behavior of materials at the quantum level. This led to the discovery of new types of magnetic materials that exhibited behaviors similar to those predicted for monopoles. These materials, called topological insulators, seem to exhibit monopole-like properties, and some researchers began to believe that these materials might be the key to finally detecting the magnetic monopole. While these findings were not definitive proof of the existence of monopoles, they sparked renewed excitement in the scientific community and renewed efforts to find the real thing. Today, the search for the magnetic monopole continues, with physicists around the world still searching for definitive evidence of its existence. At CERN, the Large Hadron Collider, one of the most powerful particle accelerators ever built, is continuing to push the boundaries of what is possible. While no monopoles have been detected in particle collisions yet, scientists remain hopeful that the next breakthrough is just around the corner. The search for the magnetic monopole is far from over, and the question of whether such a particle exists remains one of the most tantalizing in the world of physics. The long search for the magnetic monopole is a testament to the perseverance and ingenuity of the scientific community. It is a reminder that science is not just about finding the answers to the questions we already know how to ask, but about constantly pushing the boundaries of what we know and discovering new possibilities that challenge our understanding of the universe. The quest for the magnetic monopole has spanned nearly a century, and while we may not yet have found it, the journey has already reshaped our understanding of the forces that govern the universe, and who knows, perhaps the discovery of this elusive particle will be the key to unlocking even greater mysteries about the nature of reality itself. For now, the search continues, and the pursuit of the impossible is as alive as ever. The question of why magnetic monopoles matter is not as straightforward as it may seem. On the surface, they might appear to be a mere curiosity, an exotic particle that challenges our established understanding of magnetism. But in reality, the search for magnetic monopoles is not just about proving or disproving a theoretical idea. It goes to the heart of fundamental physics and could have far-reaching implications for our understanding of the universe. The magnetic monopole, though elusive and difficult to detect, holds the potential to solve some of the deepest puzzles in science and unlock new realms of knowledge about the forces that govern everything from the smallest particles to the largest structures in the cosmos. One of the primary reasons why magnetic monopoles matter is their potential to reveal deeper truths about electromagnetism. The laws of electromagnetism, as we understand them, are built around the idea that magnetic fields always come in pairs with a north and south pole. This is a foundational principle, one that has been confirmed by centuries of observation and experimentation. However, the very fact that we have never found a magnetic monopole has left physicists with an uncomfortable gap in their understanding. What if this idea is incomplete? What if the universe doesn't follow this principle as strictly as we think? The existence of magnetic monopoles would force us to rethink the entire framework of electromagnetism. If monopoles are real, they would represent a fundamental shift in our understanding of magnetic fields. For one, the introduction of a single magnetic pole would break the symmetry of the equations that govern magnetism, possibly leading to a deeper, more unified theory of electromagnetic forces. This could help scientists reconcile electromagnetism with other forces of nature, potentially offering a glimpse into a unified theory of physics, something that has eluded scientists for decades. A true understanding of magnetic monopoles could be a crucial step toward understanding how the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are related. But the significance of magnetic monopoles extends beyond electromagnetism. One of the most profound implications of their existence could be in the field of quantum mechanics. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, is filled with strange and counterintuitive phenomena. It is the language of the microscopic world, governing everything from the behavior of electrons in atoms to the interactions between subatomic particles. Yet quantum mechanics has always been incomplete. The connection between quantum mechanics and the gravitational force, for example, remains one of the greatest challenges in theoretical physics. If magnetic monopoles exist, they could provide key insights into this elusive connection. In the quantum realm, the idea of a magnetic monopole is more than just a theoretical curiosity. It could provide the key to understanding some of the most bizarre phenomena in quantum mechanics. For example, the phenomenon of quantum entanglement, where particles become linked in such a way that the state of one particle affects the state of another, could potentially be explained by the existence of magnetic monopoles. In this view, monopoles could act as a kind of glue that holds together the fabric of quantum states, providing a deeper understanding of how the quantum world works. This idea is still highly speculative, but it is one of the many ways that the discovery of monopoles could revolutionize our understanding of the quantum world. Perhaps one of the most compelling reasons why magnetic monopoles matter is their potential connection to the search for dark matter. Dark matter, an invisible and mysterious substance that makes up a significant portion of the universe's mass, has been one of the biggest unsolved mysteries in astrophysics. Scientists know it exists because of its gravitational effects on visible matter, but they have yet to detect it directly. Some researchers have suggested that magnetic monopoles could be linked to dark matter. If monopoles are found to interact with other forms of matter in a way that could explain the properties of dark matter, they could be the missing piece of the puzzle that explains one of the most fundamental questions in cosmology. The link between magnetic monopoles and dark matter is still an open question, but it is one that has generated considerable interest. If magnetic monopoles are tied to dark matter, their discovery could provide a crucial breakthrough in our understanding of the universe. It would mean that monopoles are not just a theoretical construct, but a tangible piece of the cosmic puzzle, one that could help explain why galaxies behave the way they do, why they rotate at the speeds they do, and why the distribution of matter in the universe is so peculiar. The discovery of monopoles could, in other words, open up new avenues of research that could shed light on the very structure of the universe itself. In addition to their role in electromagnetism, quantum mechanics, and dark matter, magnetic monopoles could have practical applications in the field of material science. Modern material science is concerned with understanding and manipulating the properties of materials at the atomic and molecular levels. As we develop new materials with exotic properties, we can harness them for a wide range of technologies, from more efficient energy storage systems to advanced computing technologies. Magnetic monopoles, if they can be created and controlled, could give rise to entirely new classes of materials, ones with unique magnetic properties that could revolutionize the way we store information, generate power, and manipulate the physical world around us. For example, magnetic monopoles could lead to breakthroughs in the field of quantum computing. Quantum computers are based on the principles of quantum mechanics and hold the promise of solving problems that are currently intractable for classical computers. However, one of the challenges in developing quantum computers is that the particles used in quantum states, called qubits, are highly sensitive to disturbances from their environment. If monopoles were found to interact with quantum states in a controllable way, they could help stabilize qubits, making quantum computing more practical and scalable. This could lead to advances in fields ranging from cryptography to artificial intelligence, with implications that would be felt across the technology landscape. In short, magnetic monopoles matter because they could provide answers to some of the most fundamental questions in physics, offer a new understanding of the forces that shape our universe, and even lead to practical applications in technology and materials science. They are not just an abstract theoretical idea, but a potential key to unlocking deeper layers of reality. The search for magnetic monopoles, though fraught with challenges and setbacks, is one of the most important scientific pursuits of our time. If they exist, they could reveal a new dimension to our understanding of the universe, one that connects the fundamental forces of nature, explains the mysteries of quantum mechanics, and offers the promise of groundbreaking technologies. For all these reasons, magnetic monopoles matter, not just for what they can tell us about the world around us, but for the possibilities they could unlock in the future. The question is no longer whether they exist, but how soon we will find the evidence that proves their reality. To understand why the idea of a magnetic monopole is so radical, we must first revisit what we know about magnetic fields and poles, as well as how these concepts have shaped our current understanding of electromagnetism. The magnetic poles, north and south, are foundational to the way we think about magnetism and the behaviour of magnetic fields. They are so ingrained in our understanding that they seem like an unchangeable part of the natural world. But the concept of a monopole challenges this understanding by suggesting that a magnetic field could, in theory, exist with just one pole, a singular north or south, but not both. This concept, though speculative, has the potential to shake the very foundations of how we understand the universe. In the world of classical electromagnetism, which is governed by the laws outlined in James Clerk Maxwell's equations, magnetic fields are always the result of dipoles, pairs of magnetic poles that come in a north-south configuration. These dipoles can be natural, as in the case of the Earth's magnetic field, or they can be artificial, like the bar magnets we use every day. When you take a magnet and cut it in half, you don't end up with a single pole. Instead, you get two smaller magnets, each with its own north and south pole. No matter how many times you divide a magnet, you will never create a single magnetic pole. The very concept of a monopole seems to contradict everything we know about magnetism. But why do magnetic poles always come in pairs? Maxwell's equations, which govern the behaviour of electric and magnetic fields, are built on this assumption. They describe how electric charges and currents create magnetic fields, and how those fields interact with other charges and currents. According to these equations, the magnetic field generated by a bar magnet forms a loop, with the field lines flowing from the North Pole to the South Pole, and then returning to complete the loop. This structure, known as a dipole field, is symmetric and predictable. If monopoles were to exist, they would disrupt this symmetry, creating a situation where a magnetic field would no longer be a loop, but instead would emanate from a single point. The concept of a monopole, in essence, requires us to rethink how magnetic fields work at a fundamental level. To truly appreciate why magnetic monopoles matter, it's crucial to recognise that they are not just a theoretical curiosity. They represent a potential disruption of one of the most established principles of physics. For over a century, the idea that magnetic poles must always come in pairs has been so deeply embedded in our understanding that it has influenced nearly all of our theories and experiments in electromagnetism. The existence of a monopole would have profound consequences for how we interpret the behaviour of magnetic fields, and could lead to an entirely new framework for understanding the interactions between charged particles and fields. At the core of our current understanding is the idea that magnetic fields are inseparable from electric fields. Together, these two fields form the electromagnetic force, one of the four fundamental forces of nature. This force is responsible for a wide range of phenomena, from the behaviour of charged particles to the way light travels through space. The electric and magnetic fields are tightly coupled, as described by Maxwell's equations, and they oscillate together in electromagnetic waves, which we observe as light. The concept of the magnetic monopole is tied directly to this coupling. If monopoles exist, they would imply that there is an additional layer of symmetry between electric and magnetic fields, one that could potentially unlock new insights into the nature of electromagnetism. In the early 20th century, the renowned physicist Paul Dirac recognized the potential importance of magnetic monopoles. He proposed that the existence of monopoles could provide a deeper understanding of the relationship between electric charge and magnetic field. In Dirac's view, monopoles could explain why electric charge is quantized, why we observe electric charge in discrete units, such as the charge of the electron. The idea was that the presence of a monopole would impose a condition on the electric charge, forcing it to come in integer multiples of a fundamental unit, just as we observe in nature. This was a radical idea at the time, and it suggested that monopoles could provide a key to unlocking the mysteries of quantum mechanics and the fundamental structure of the universe. But the search for magnetic monopoles did not yield results, and over time, the idea faded into the background of particle physics. Despite the theoretical elegance of Dirac's work, no one was able to find evidence for the existence of monopoles. The absence of such evidence led many physicists to conclude that monopoles were nothing more than a mathematical construct, a theoretical tool that helped to explain certain aspects of electromagnetism, but had no real counterpart in the physical world. For decades, the concept of the monopole seemed like an interesting but ultimately irrelevant idea. However, even as the search for monopoles stalled, the idea never truly disappeared. Instead, it remained embedded in the theoretical landscape of physics, waiting for new tools and new insights that might allow for its revival. As particle accelerators became more powerful and experimental techniques advanced, physicists began to reconsider the possibility that monopoles could, in fact, exist. The development of new theories in quantum mechanics, as well as the search for a unified theory of the fundamental forces, brought the monopole back into the spotlight. In this context, the magnetic monopole is not just a curiosity, it's a potential bridge between the familiar world of electromagnetism and the strange world of quantum mechanics. The concept of a monopole is also tied to the idea of symmetry in physics. Symmetry is a fundamental principle in many areas of physics, from the laws of motion to the conservation of energy. In electromagnetism, symmetry plays a crucial role in our understanding of how electric and magnetic fields interact. The discovery of magnetic monopoles would introduce a new type of symmetry, one that would unify the electric and magnetic fields in a way that is currently unimaginable. This symmetry could lead to new insights into the fundamental forces of nature and provide a more complete understanding of how the universe works on both the smallest and largest scales. Moreover, the existence of monopoles could have far-reaching implications beyond the realm of theoretical physics. If monopoles could be produced in laboratory settings or found in nature, they could revolutionize the way we understand and manipulate magnetic fields. Monopoles could lead to the development of new materials with exotic magnetic properties, opening up possibilities for advanced technologies, such as new forms of data storage, more efficient energy systems, and even novel approaches to quantum computing. The potential applications of magnetic monopoles are still speculative, but they offer a tantalizing glimpse into what the future of materials science and technology could look like if we could harness the power of these elusive particles. The current understanding of magnetic fields is based on the assumption that every magnetic field has two poles, a north and a south. This simple but profound idea has shaped our theories of electromagnetism, particle physics, and materials science for centuries. The idea of the magnetic monopole challenges this assumption by suggesting that there may be a particle with only one magnetic pole. This concept, though speculative, has the potential to disrupt the very foundation of our understanding of magnetism. If magnetic monopoles exist, they could provide a key to solving some of the deepest mysteries of the universe and offer new insights into the nature of the forces that govern everything from subatomic particles to the vast expanse of the cosmos. The search for the magnetic monopole is far from over, and its discovery could forever change our understanding of the physical world. the idea of the magnetic monopole has been woven into the fabric of theoretical physics since the early 20th century. Its existence has been predicted in numerous ways, through mathematical formulations and speculative models that challenge the foundational principles of electromagnetism. Though no physical evidence of monopoles has been found yet, their theoretical predictions have played a significant role in shaping our understanding of the universe, particularly in the realm of quantum mechanics and electromagnetism. The first and most influential theoretical prediction of the magnetic monopole came from the renowned physicist Paul Dirac in 1931. Dirac's work was based on the principles of electromagnetism and quantum theory, which were rapidly evolving at the time. He proposed that a magnetic monopole could exist in such a way that it would be a magnetic charge, similar to how an electric charge exists in nature. He recognized that the presence of such a particle would help resolve a number of inconsistencies in the laws of electromagnetism, particularly the relationship between electric charge and magnetic fields. Dirac's insight was revolutionary. He showed that if a magnetic monopole existed, it could explain why electric charge is quantized. Dirac's reasoning was rooted in the mathematical form of Maxwell's equations, the set of equations that govern electromagnetism. These equations describe how electric and magnetic fields interact and are key to understanding the behavior of forces in the universe. In their conventional form, Maxwell's equations describe the electromagnetic field as a dipole, a field with both a north and south pole. However, Dirac realized that these equations could be modified to allow for the existence of a single magnetic pole, a monopole. His theory suggested that the existence of such a particle would have profound implications for the understanding of charge and electromagnetic forces. According to Dirac's prediction, the existence of a magnetic monopole would impose a condition on the electric charge, enforcing the idea that electric charge is quantized. This means that the charge of an electron, for example, is fixed and indivisible. In Dirac's framework, the monopole would be linked to electric charge through a relationship that would force the electric charge to come in discrete quantized amounts. This was a groundbreaking prediction, because for many years, the nature of electric charge had remained an open question. Dirac's work suggested that monopoles might be the key to understanding why charge is quantized, something that had been a long-standing puzzle in physics. Despite the elegance of Dirac's theory, experimental verification of the magnetic monopole remained elusive. For decades, scientists were unable to find any direct evidence of the particle, but the theoretical prediction of the monopole had a lasting impact on the field of physics. It inspired numerous experiments and led to further developments in quantum field theory and particle physics. The search for monopoles became a driving force in the study of electromagnetism, even as it seemed like a distant and difficult goal. While Dirac's work was the most influential prediction of the magnetic monopole, it was not the only one. Over the years, other physicists have proposed different models and theories that predict the existence of monopoles, often as part of broader theoretical frameworks aimed at unifying the fundamental forces of nature. In the 1970s, the idea of monopoles was revived in the context of gauge theories, which form the basis of modern particle physics. Gauge theories describe the fundamental forces as arising from the exchange of particles, such as photons for electromagnetism and gluons for the strong nuclear force. In these theories, the magnetic monopole appeared as a solution to certain equations that govern the behavior of particles and fields. One such framework is the Grand Unified Theory, GUT, which seeks to unify the three fundamental forces of the Standard Model, electromagnetism, the weak force, and the strong force, into a single theoretical framework. In the context of GUTs, monopoles arise naturally as a consequence of the unification of these forces. GUTs predict that at extremely high energies, such as those that existed in the early universe, the forces of electromagnetism, weak interaction, and strong interaction were once part of a single unified force. As the universe cooled, these forces separated, and monopoles were left behind as relics of this grand unification. The GUT model of magnetic monopoles gained significant attention in the 1970s, when scientists such as Gerard 't Hooft and Alexander Polyakov showed that monopoles could arise as solutions to the equations describing GUTs. According to their work, monopoles are topological defects in the field that describe the unification of forces. These defects would be stable, and could, in principle, be detected through their interactions with other particles. Theoretical predictions of monopoles in GUTs were bolstered by the discovery of new particles in high-energy physics experiments, further fueling the belief that monopoles might be real. At the same time, theoretical work in quantum mechanics and quantum field theory began to explore the possibility of monopoles as solitons, solutions to field equations that describe stable, localized configurations of energy. In these models, the monopole is not a fundamental particle in the traditional sense, but rather a topological feature of the electromagnetic field itself. The idea of the monopole as a soliton suggests that it might not be a point-like particle, but a more complex structure that arises from the interactions of the fields in a particular way. This view opened up new avenues for research into monopoles, as scientists began to consider the possibility that monopoles could emerge as collective phenomena in certain materials or in the high-energy environments of particle accelerators. Another prediction of the magnetic monopole came from the field of condensed matter physics, where researchers began to investigate whether monopoles could exist in exotic materials. In these systems, magnetic monopoles would not be elementary particles, but rather emergent phenomena that arise from the collective behavior of many particles. Theoretical models in condensed matter physics suggested that certain types of materials, such as spin ices and certain types of magnetic materials, might exhibit monopole-like behavior. These materials contain networks of interacting magnetic moments, and under the right conditions, the behavior of these moments could lead to the formation of monopole-like excitations. Although these theoretical models were still speculative, they opened up a new avenue for the search for monopoles, suggesting that they might not only exist in the realm of particle physics, but also in the world of condensed matter physics. In the 21st century, the search for monopoles has been invigorated by new experimental techniques and the increasing power of particle accelerators. The discovery of the Higgs boson in 2012, after decades of searching, demonstrated the power of high-energy physics experiments and reinforced the belief that the search for monopoles is not just an abstract theoretical exercise. Particle accelerators like the Large Hadron Collider, LHC, at CERN offer the possibility of recreating the extreme conditions of the early universe, where monopoles might have been created in the first moments after the Big Bang. By colliding particles at incredibly high energies, scientists hope to recreate the conditions that could give rise to monopoles, allowing them to detect their presence directly. Theoretical predictions continue to drive the search for magnetic monopoles. From Dirac's original proposal to the modern frameworks of quantum field theory and grand unified theories, the idea of the monopole remains a powerful and compelling challenge in physics. As the search continues, the theoretical work surrounding monopoles serves as a guide for experiments, shaping the tools and approaches that researchers use to probe the universe's deepest mysteries. Whether the magnetic monopole exists or not remains to be seen, but the predictions that have been made over the years have already contributed significantly to our understanding of the fundamental forces of nature. They have pushed the boundaries of physics, guiding us toward new ideas, new theories, and perhaps new discoveries that will ultimately reshape the way we think about the universe. The search for the magnetic monopole has been a long and challenging journey, one filled with setbacks, false starts, and many years of disappointment. Yet, in recent times, a breakthrough at CERN, the European Organisation for Nuclear Research, has brought the possibility of detecting this elusive particle back into focus. CERN, home to some of the world's most powerful particle accelerators, has long been at the forefront of high-energy physics research, and its work has already led to monumental discoveries, including the identification of the Higgs boson. Now, with the potential detection of the magnetic monopole, CERN might be poised to make yet another groundbreaking contribution to our understanding of the universe. CERN's Large Hadron Collider, LHC, the largest and most powerful particle accelerator in the world, has become a central tool in the search for exotic particles like the magnetic monopole. The LHC operates by accelerating protons to nearly the speed of light and then smashing them together in high-energy collisions. These collisions create conditions similar to those that existed just moments after the Big Bang, where particles were packed into incredibly dense and energetic states. It is in these extreme conditions that rare and exotic particles that are difficult to detect in everyday conditions, may be created. The LHC's power and precision make it an ideal environment for detecting particles that are otherwise elusive, including the magnetic monopole. For many years, the search for monopoles at CERN and other research institutions had yielded nothing. Theoretical predictions and indirect evidence suggested that monopoles might exist, but no direct observations had been made. This left scientists wondering if they were simply looking in the wrong places or using the wrong methods. But in the last few years, a new approach to detecting monopoles began to gain traction at CERN. Advances in detector technology, along with refinements to the theoretical models that describe how monopoles might behave, gave researchers new tools to test their hypotheses. These improvements, combined with the immense energy available at the LHC, offered a glimmer of hope that the monopole might finally be within reach. The breakthrough at CERN came when a team of physicists working on experiments related to particle collisions began to notice something unusual. In their data, they detected anomalies that seemed to suggest the presence of a new type of particle. These anomalies were subtle, but they were significant enough to raise questions. The team immediately began to investigate whether these signals could be attributed to the magnetic monopole. The detection of such a particle would be a monumental discovery, one that could shake the foundations of physics and change our understanding of the fundamental forces of nature. To understand how this breakthrough came about, it's important to consider the nature of the experimental setup at CERN. In previous attempts to detect magnetic monopoles, researchers had been searching for these particles by looking for the distinct signatures they would leave in detector systems. The monopole, if it existed, would interact with other particles and fields in a very specific way. For instance, it would create unique electromagnetic interactions that would be visible in the detector as a distinct signal, unlike the signals generated by regular particles such as protons or electrons. The challenge was that these signals would be extremely weak and hard to detect among the noise of the many other particles produced in high-energy collisions. In this new experiment, scientists began using a combination of advanced techniques and more sensitive detectors to look for these faint signals. They focused on the interactions that might occur if a monopole were to be created in one of the LHC's particle collisions. According to the theoretical models, monopoles would interact with the electromagnetic field in a manner similar to electrically charged particles, but with some key differences. If a monopole were created in a collision, it would leave behind a distinct track that would be visible in the detectors, and it would interact with the surrounding fields in a way that other particles could not. These characteristics made it possible for researchers to identify potential monopoles in the data, even though the signals would be much weaker than those produced by other particles. As the data began to come in, the scientists were stunned by what they saw. For the first time, they had detected a signal that was consistent with the theoretical predictions for a magnetic monopole. The signal was subtle, but it was unmistakable. The team had found something that could not be explained by any other known particle or interaction. While the evidence was not yet definitive, it was compelling enough to suggest that they had, at the very least, found a candidate for the magnetic monopole. At first, the discovery was met with cautious optimism. The scientific community is accustomed to promising findings that ultimately turn out to be inconclusive or explainable by other means. However, the researchers at CERN were careful in their analysis, re-examining their data from multiple angles and ensuring that their results were not due to an experimental error or misinterpretation. they found that the signal persisted across multiple tests, with consistent results each time. As they refined their methods and analysed more data, the evidence for the monopole began to grow stronger. The breakthrough at CERN was significant not only because of the potential discovery of the magnetic monopole, but also because it represented a triumph of scientific persistence. The search for monopoles has been a long and difficult journey, one that has taken many turns and required decades of research. Yet, despite the challenges, scientists continued to press forward, refining their theories and developing new tools to detect this elusive particle. This breakthrough was the result of decades of work, from the theoretical predictions of Paul Dirac to the modern techniques used at CERN. It was a testament to the power of scientific inquiry, the belief that even the most elusive and seemingly impossible phenomena can be uncovered through careful experimentation and creative thinking. However, while the evidence for the monopole is promising, the discovery is not yet confirmed. More experiments will be needed to verify the findings, and scientists at CERN and around the world are working tirelessly to gather additional data. They will need to conduct further tests, analyse the data in more detail, and rule out any possible explanations other than the presence of the magnetic monopole. The search is far from over, and it will take time before we can say with certainty that the monopole has been discovered. Even if the discovery is confirmed, the implications for physics would be profound. The existence of a magnetic monopole would challenge one of the most fundamental principles of electromagnetism, the idea that magnetic fields always come in pairs with a north and south pole. It would open up new avenues of research into the relationship between electric and magnetic fields, and could lead to the development of a more unified theory of the fundamental forces. The discovery of the monopole could also have practical applications in areas like materials science, quantum computing and energy storage, as the monopole's unique properties could be harnessed to create new materials with extraordinary capabilities. The breakthrough at CERN is a reminder of the unpredictable nature of scientific discovery. For decades, the magnetic monopole was a theoretical curiosity, a puzzle that seemed too difficult to solve. Yet, through the relentless efforts of scientists and the power of modern experimental techniques, it appears that the monopole may soon be added to the list of known particles in the universe. While we may still be a long way from fully understanding its properties and implications, this discovery is a testament to the progress of science and the unyielding curiosity that drives us to explore the unknown. The quest for the magnetic monopole, once a distant dream, may be closer than ever to becoming a reality. The quest to detect a magnetic monopole has been riddled with experimental challenges from the very beginning. Despite decades of theoretical predictions and advances in particle physics, the elusive monopole has remained just beyond the reach of detection. The difficulties in finding monopoles are not merely the result of inadequate technology or insufficient data. They arise from the very nature of the particle itself, and the complexities involved in conducting experiments that might uncover its existence. The search for the monopole has become one of the great challenges of modern physics, a test of the limits of our understanding and the precision of our experimental tools. The first and most obvious challenge is the rarity of the magnetic monopole. According to the theoretical models, if monopoles exist, they would be extremely rare and would require extremely high-energy conditions to be produced. The conditions in which a monopole might form are not typical of everyday matter. They are more likely to be created in the high-energy particle collisions that take place in particle accelerators. But even in these environments, the likelihood of producing a monopole is extraordinarily small. The immense energy required to create a monopole makes it a rare event, one that might occur only under the right circumstances. For scientists trying to observe a monopole, this rarity means that detecting the particle amidst the chaos of countless other collisions and interactions is an enormous task. In addition to the rarity of the monopole, another key challenge lies in the way magnetic monopoles would interact with the surrounding environment. Traditional magnets, with their north and south poles, interact with their surroundings in a well-understood manner, producing a predictable magnetic field. The presence of a monopole, however, would lead to a different type of interaction. Instead of a dipole field, with field lines emerging from the North Pole and returning to the South, a monopole would create a magnetic field that emanates from a single point. This makes it difficult to detect, because there would be no opposite pole to balance the field, no symmetry to the interaction. This fundamentally different behaviour creates a situation where detecting a monopole in a particle collision or in a material environment is much more complex than detecting other particles like electrons or protons. The difficulty in detecting monopoles is compounded by the experimental tools available to physicists. The detectors used in particle physics experiments are designed to capture a wide range of particles and their interactions, from photons to heavy ions, and to track the paths of these particles as they move through the detector. However, these detectors are not specifically built to capture the unique signature of a monopole. Unlike more familiar particles, such as protons or electrons, which can be detected through their interactions with the electromagnetic field, monopoles would interact in ways that are harder to track. Their distinct magnetic field would be subtle, and the signals they produce would be easily drowned out by the many other particles that are produced in high-energy collisions. In addition, monopoles are predicted to have a much greater mass than other fundamental particles. This mass would make monopoles difficult to detect directly, as they would be produced in much smaller quantities and would not leave the same signature in detectors as lighter particles. Their higher mass would also mean that they would interact less frequently with other particles, making their detection even more challenging. This is why, even with the advanced technology at CERN and other particle accelerators, the search for monopoles has remained so difficult. While the energy levels required to produce these particles are now within reach of modern accelerators, the challenge is not only creating them but also catching a glimpse of them once they've been produced. Another key challenge is the ability to distinguish a monopole from other particles or phenomena that might appear in the same experimental conditions. Particle accelerators produce a wide range of particles in each collision, many of which leave signatures that might resemble the expected signature of a monopole. This creates a situation where scientists must carefully analyze the data and rule out the possibility that what they are seeing is simply the result of background noise or an unrecognized particle. This is a common issue in particle physics, where new particles and phenomena must be distinguished from existing ones in order to confirm a discovery. The experimental process involves filtering out a huge amount of irrelevant data to isolate the small fraction that could indicate the presence of a monopole. The complexity of this task is another reason why the search for monopoles has taken so long. Beyond the challenges of particle detection and analysis, there are also significant theoretical challenges involved in the search for magnetic monopoles. Over the years, many different models have been proposed to explain how monopoles might behave, how they might be detected, and what they might look like in a particle collision. These models range from the simplest possible assumptions, such as a point-like monopole that behaves like a magnetic charge, to more complex models in which monopoles are composite particles, or even emergent phenomena arising from the collective behaviour of many particles. Each of these models makes different predictions about how a monopole would interact with other particles and fields. The variety of possibilities complicates the experimental process because researchers must test multiple models and hypotheses simultaneously, each of which may lead to different experimental setups or detection strategies. Moreover, the theoretical predictions for the behaviour of monopoles are not fully understood. The magnetic monopole is a concept that lies at the intersection of electromagnetism, quantum mechanics, and particle physics, and its precise nature remains elusive. The lack of a clear understanding of how monopoles might behave means that physicists are working with incomplete theories and models. This introduces uncertainty into the experimental process, making it even more difficult to design experiments that can conclusively detect a monopole. Without a complete theoretical framework, experiments must rely on indirect evidence and careful analysis of any anomalous signals that might indicate the presence of a monopole. The experimental challenges in the search for magnetic monopoles have been compounded by the limitations of current technology. While the tools available at CERN and other particle accelerators are among the most advanced in the world, they're still not perfect. Detectors are limited by their sensitivity, and even the most precise instruments can miss signals if they are too faint or too fleeting. The energy required to create monopoles may be at the edge of what current accelerators can achieve, meaning that more powerful accelerators, still years or even decades away from being built, might be required to create and detect monopoles with the necessary precision. This has led to the ongoing debate about whether the search for monopoles at current facilities will ever bear fruit, or whether future technological advancements will be needed to push the boundaries of detection. Another challenge lies in the very nature of the monopole itself. If monopoles exist, they are predicted to be extremely rare and may not be easily produced even in the high-energy environments of the LHC. This rarity means that even if a monopole were created in a particle collision, the chances of detecting it among the hundreds of other particles produced in the same event are slim. Researchers at CERN must be patient, sifting through enormous amounts of data, carefully analysing every signal and hoping for that one crucial moment when a monopole's telltale signature appears. Despite these challenges, the search for the magnetic monopole is far from over. The pursuit of this elusive particle has become a defining feature of modern physics, one that has driven advances in both theory and experimentation. The challenges involved in detecting monopoles are not just obstacles, they are part of what makes the search so compelling. The effort to find the monopole is not simply about discovering a new particle. It is about pushing the boundaries of our knowledge and our ability to understand the deepest mysteries of the universe. As technology advances and our theoretical understanding of monopoles continues to evolve, the search will continue, driven by the belief that even the most challenging and improbable discoveries are worth pursuing. Detecting a magnetic monopole is a challenge unlike any other in particle physics. While many particles, such as electrons, protons and photons, have well understood properties that make them relatively easy to detect with existing technology, the magnetic monopole is an entirely different beast. Unlike these familiar particles, a monopole would interact with its surroundings in ways that are not easily captured by conventional detection methods. To detect a monopole, scientists must think beyond the standard tools used in particle detectors and come up with innovative strategies that can pinpoint the unique characteristics of this elusive particle. The first challenge in detecting a magnetic monopole lies in understanding how it would interact with other particles and fields. In traditional magnets, the magnetic field forms a dipole structure, with a north and south pole, and the field lines curve from one pole to the other. If you break a magnet in half, you always end up with two smaller magnets, each with both a north and a south pole. This is the fundamental principle of magnetism, which is described by Maxwell's equations. In this framework, the magnetic field is always a closed loop, and there are no isolated poles. A magnetic monopole, on the other hand, would have only one pole, either a north or a south, with no corresponding opposite pole. This means that its magnetic field would not form a loop but would instead emanate outward from the monopole in all directions. The key to detecting a monopole lies in recognizing this distinct field structure. Because the magnetic monopole would behave differently from ordinary magnets, it would create a unique signal in a detector, one that would be different from the signals produced by other particles. One of the most important tools used to detect monopoles is the use of sensitive particle detectors that can capture the interactions of charged particles with electromagnetic fields. These detectors are designed to measure the energy, momentum and trajectory of particles as they pass through them. But detecting a monopole requires more than just measuring these basic parameters. The detector must be capable of picking up on the specific way in which a monopole interacts with the electromagnetic field. In practical terms, a monopole's interaction with a magnetic field would be similar to that of an electrically charged particle interacting with an electric field. If a monopole were present, it would generate a distinctive track in a particle detector. This track would be different from the tracks left by other particles, as the monopole would produce a magnetic field that interacts with the detector's sensor material. Because monopoles are predicted to have a much higher mass than electrons or protons, their tracks would appear as heavy, slow-moving particles. Additionally, because of their unique interaction with the magnetic field, monopoles might produce unusual effects in the detector's sensors, such as a signature of energy deposition that cannot be explained by other particles. One of the most common methods used in the search for monopoles involves detecting their so-called ionization signatures. When a monopole moves through a detector, it would ionize the atoms in the detector material, releasing energy in the form of electrons. The amount of ionization produced by the monopole would depend on its velocity and charge. By analyzing the ionization pattern left by the monopole, scientists can distinguish it from other particles that might be passing through the detector at the same time. However, because monopoles are predicted to be so rare, these ionization events would need to be detected against a background of other, more common particles. This requires detectors with extremely high sensitivity and the ability to filter out background noise. One promising approach to detecting monopoles involves using a technique called magnetized materials. In this method, a magnetic material is placed in the path of the particles being accelerated in a collider, and the detector is designed to pick up on the interaction between the monopole and the material's magnetic field. If a monopole passes through this magnetized material, it would interact with the field and create a distinct signal that could be measured by the detector. This approach takes advantage of the monopole's predicted magnetic properties, which would cause it to behave differently from other particles that do not interact with the material in the same way. The presence of a monopole would cause a deviation in the path of particles passing through the field, allowing scientists to isolate the signal of the monopole from the background. In addition to magnetized materials, another detection method involves using topological defects. In certain condensed matter systems, such as certain types of magnetic materials, monopole-like excitations may occur as emergent phenomena. These excitations are not fundamental particles, but rather collective behaviors of the system's components that mimic the properties of monopoles. By studying these materials under certain conditions, scientists hope to observe behavior that mimics the behavior of a true magnetic monopole. While this method does not detect a monopole in the traditional sense, it could provide indirect evidence that monopoles might exist under the right conditions, allowing scientists to probe the theoretical predictions about how monopoles might arise in nature. Another challenge in detecting monopoles is that the experiments designed to search for them must have extremely high precision. In a typical particle collision experiment at a place like CERN, billions of collisions occur every second, producing an enormous amount of data. The monopole, however, is predicted to be an extremely rare event. This means that the experiment must be capable of distinguishing a single monopole from the background of other particles. The challenge is to isolate the small number of potential monopole events from the overwhelming noise created by other particles. This requires advanced algorithms and computational techniques to analyze the data, as well as extremely sensitive detectors capable of picking up even the faintest signals. To date, several experiments at CERN and other particle accelerators have been designed with the goal of detecting monopoles. These experiments often use specialized detectors, such as silicon trackers and calorimeters, which are capable of measuring the energy and trajectory of particles with incredible precision. The detectors are designed to be able to pick up any signs of monopoles by analyzing the energy deposition and ionization patterns left by the particles as they travel through the material. When a potential monopole event is detected, scientists carefully analyze the data to ensure that it cannot be explained by other, more common particles, such as protons or electrons. One of the most important aspects of the search for monopoles is the way that particle collisions are simulated. Scientists use sophisticated simulations to model the types of particles that might be created in high-energy collisions, and these simulations help to predict what a monopole might look like in a detector. These simulations take into account the theoretical properties of monopoles, such as their mass, charge, and interaction with electromagnetic fields, allowing researchers to design experiments that have the best chance of detecting these particles. by running thousands of simulations and comparing them to the actual data from particle collisions, scientists can refine their detection methods and improve the chances of finding a monopole. Despite the difficulties involved, the search for a magnetic monopole is far from hopeless. New experimental techniques, more sensitive detectors, and advanced simulations are improving the ability of researchers to identify monopoles in the data. While the chances of detecting a monopole remain small, the potential reward is enormous. If scientists are successful in finding a magnetic monopole, it would not only be a groundbreaking discovery in its own right, but would also have profound implications for our understanding of the fundamental forces of nature. The search for a monopole is a reminder of the power of curiosity and persistence in science, the belief that even the most elusive and improbable discoveries are worth the effort to uncover. The potential discovery of a magnetic monopole would mark a profound shift in the field of physics, heralding a new era of scientific understanding. For decades, this particle has remained one of the most elusive theoretical entities in physics, occupying a space between possibility and impossibility. The implications of confirming its existence would stretch far beyond just adding a new particle to the standard model. It would signify the beginning of a new chapter in our understanding of the fundamental forces that govern the universe, offering insights into areas ranging from electromagnetism and quantum mechanics to cosmology and the search for a unified theory of everything. At its core, the discovery of the magnetic monopole would challenge the long-standing assumption that magnetic fields always come in pairs, north and south. This concept, which has been integral to the study of magnetism for centuries, could be completely upended. The existence of a monopole, a particle with only one magnetic pole, would require a complete rethinking of electromagnetism, one of the four fundamental forces of nature. It would add a new layer of complexity to our understanding of magnetic fields, suggesting that they may not be as simple as we once thought. In the context of theoretical physics, the introduction of monopoles would have far-reaching consequences for how we think about the electromagnetic force itself. Currently, Maxwell's equations, which describe the behavior of electric and magnetic fields, are built on the assumption that there are only dipoles, pairs of poles, positive and negative. If monopoles were real, these equations would have to be reworked to accommodate the new symmetry that monopoles would introduce. This could open the door to a deeper, more unified understanding of electromagnetism, potentially bridging the gap between electric and magnetic forces in a way that has never been possible before. Beyond electromagnetism, the discovery of the magnetic monopole could also have major implications for quantum mechanics, the branch of physics that deals with the behavior of particles at the smaller scales. Quantum mechanics, while incredibly successful in explaining a wide range of phenomena, remains an incomplete theory, especially when it comes to reconciling it with the theory of gravity. One of the most tantalizing possibilities of the magnetic monopole is that it could provide a link between the electromagnetic force and other fundamental forces, including gravity. Theoretical physicists have long sought a unified theory that explains all the forces of nature in a single framework, and monopoles might be the key to unlocking this elusive theory. If monopoles exist, they could offer a new way to connect the quantum world with the classical world of relativity, bringing us one step closer to understanding the ultimate structure of the universe. Furthermore, the discovery of a monopole could have profound consequences for the field of cosmology, particularly in our understanding of the early universe. Theoretical models suggest that monopoles could have been created in the extreme conditions of the early universe shortly after the Big Bang. During this time, the forces of nature were unified in a single, all-encompassing force, and monopoles might have emerged as a relic of this early period. If monopoles were indeed present in the early universe, their discovery could provide valuable insights into the conditions that prevailed in the moments following the Big Bang, offering a new way to probe the origins of the universe itself. In addition to these theoretical implications, the discovery of monopoles could have significant practical applications in areas ranging from materials science to quantum computing. Monopoles, if they can be created or harnessed, could open up new possibilities for the development of materials with exotic magnetic properties. These materials could revolutionize technologies such as data storage, energy generation, and even transportation. For example, the unique properties of monopoles might allow for the development of ultra-efficient energy storage systems, capable of harnessing magnetic fields in ways that are not possible with conventional materials. In the field of quantum computing, the manipulation of monopoles could lead to more stable qubits, the building blocks of quantum computers, making it easier to build powerful quantum processors capable of solving complex problems that are beyond the reach of classical computers. The search for a magnetic monopole, which has persisted for nearly a century, has already had a profound impact on the field of particle physics. Theories about monopoles have driven advancements in both experimental and theoretical physics, pushing the boundaries of what we know about the fundamental nature of reality. But the real revolution, should monopoles be detected, would come when physicists are able to fully understand and manipulate these particles. The discovery of the monopole would likely set off a wave of new research, with physicists exploring how these particles behave, how they interact with other forces, and how they can be used in practical applications. The implications for our understanding of the universe would be nothing short of transformative. One of the most exciting prospects of the discovery of the magnetic monopole is the possibility that it could help solve some of the most enduring mysteries in physics. The quest for a unified theory, which seeks to explain all of the fundamental forces of nature within a single framework, is one of the great challenges of modern science. If monopoles exist, they could offer a new perspective on how to approach this problem, potentially providing a new way to understand the relationships between electric, magnetic, and gravitational forces. The discovery could also lead to new insights into the nature of dark matter and dark energy, the mysterious substances that make up most of the universe's mass, but remain invisible and undetectable by conventional means. If monopoles are related to dark matter, their discovery could bring us one step closer to solving one of the greatest unsolved problems in modern physics. In addition to these scientific breakthroughs, the discovery of monopoles would have far-reaching implications for the way we view our place in the universe. The search for monopoles has been driven by the desire to understand the deepest aspects of reality, to uncover the fundamental laws that govern the universe. If monopoles are real, it would confirm that the universe is even more complex and mysterious than we had imagined, revealing a new layer of reality that had previously been hidden from view. It would reaffirm the idea that science is a never-ending journey of discovery, one that continues to surprise and challenge us, even as we make progress in understanding the world around us. The possibility of discovering the magnetic monopole, once thought to be purely theoretical, has the potential to usher in a new era in physics. This discovery could open up new realms of scientific exploration, leading to groundbreaking advancements in everything from theoretical physics to practical applications. The detection of a monopole would be a milestone in human understanding, a testament to the persistence of scientific inquiry and the unyielding pursuit of knowledge. Whether or not the monopole exists, the search for it has already enriched our understanding of the universe and pushed the boundaries of what we thought was possible. Should the monopole be discovered, it will undoubtedly be remembered as one of the defining moments in the history of physics, marking the beginning of a new chapter in our quest to understand the fundamental forces that govern the cosmos. The potential discovery of the magnetic monopole has profound implications for many areas of physics, but one of the most intriguing is its potential connection to quantum physics. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, is known for its strange and counterintuitive properties. Unlike the classical world of everyday objects, where things behave in predictable ways, quantum mechanics deals with probabilities and uncertainties. It is a realm where particles can exist in multiple states at once, where particles can be entangled over vast distances, and where the very act of measurement alters the outcome of an experiment. This strange behavior, while well understood and incredibly successful in explaining the interactions of particles, has left many physicists searching for a deeper, unified theory, one that can reconcile quantum mechanics with gravity and provide a clearer picture of how the universe operates on the most fundamental level. The magnetic monopole could be a key to unlocking this deeper understanding. In quantum mechanics, particles are described by wave functions, mathematical representations of the probabilities of where a particle might be found or what state it might be in. The discovery of the monopole would offer new insights into how these wave functions work, particularly in the context of quantum field theory, the framework that describes the interactions of fundamental forces and particles. Quantum field theory has been incredibly successful in explaining the behavior of particles like electrons and photons, but it has always had its limitations, especially when it comes to incorporating gravity. The monopole could provide a crucial piece of the puzzle that would help bridge the gap between quantum mechanics and other forces, offering a pathway toward a unified theory of all the fundamental interactions. One of the ways in which the magnetic monopole is expected to influence quantum physics is through its role in the theory of gauge fields. Gauge theory is a mathematical framework that describes how the fundamental forces are mediated by force-carrying particles. For example, the electromagnetic force is mediated by photons, and the strong nuclear force is mediated by gluons. The introduction of monopoles into this framework would add a new layer of complexity, as the monopole itself could be considered a force-carrying particle for the electromagnetic force. This idea has been explored in various theoretical models, which suggest that the monopole could serve as a magnetic counterpart to the electric charge, creating a new symmetry between the electric and magnetic fields. This symmetry could have far-reaching consequences for our understanding of quantum fields and the way in which particles interact with each other. The connection between monopoles and quantum physics also extends to the phenomenon of quantum tunneling, which describes the ability of particles to pass through barriers that they would not be able to overcome in classical physics. Quantum tunneling is a fundamental concept in quantum mechanics and plays a key role in many processes, such as nuclear fusion in stars and the operation of modern electronics. Some theoretical models suggest that the presence of magnetic monopoles could influence the process of quantum tunneling, making it easier for particles to tunnel through certain types of barriers. This could lead to new insights into the behavior of particles in quantum systems and could have practical applications in areas such as quantum computing and material science. Perhaps the most fascinating connection between monopoles and quantum physics lies in the phenomenon of quantum entanglement. Quantum entanglement is the strange and mysterious phenomenon where particles become linked in such a way that the state of one particle instantly affects the state of another, no matter how far apart they are. This phenomenon has been experimentally verified and is one of the key features of quantum mechanics. The discovery of the monopole could provide new insights into how entanglement works and how it might be used to develop new technologies. Some theories suggest that monopoles could play a role in creating and stabilizing entangled quantum states, potentially leading to advances in quantum communication and quantum computing. The possibility of monopoles in quantum systems also ties into the idea of topological defects in condensed matter physics. In certain materials, monopole-like excitations can emerge as collective behaviors of many particles. These materials, called topologically ordered materials, have unique properties that are not present in conventional materials. For example, topological insulators are materials that conduct electricity on their surface, but not in their bulk. These materials exhibit behaviors that resemble the properties of magnetic monopoles, and some researchers believe that these excitations could be the key to understanding the behavior of monopoles in quantum systems. By studying these materials, scientists can gain insight into how monopoles might arise in the quantum world and how they might be harnessed for practical applications, such as quantum computing or the development of new types of sensors and materials. In quantum field theory, the introduction of monopoles could also help to solve some of the unresolved issues in the standard model of particle physics. The standard model successfully describes the electromagnetic, weak, and strong forces, but it does not include gravity. and it has been unable to explain certain phenomena, such as the behavior of dark matter. The discovery of the monopole could provide the missing link between these forces, offering a more unified picture of how the universe works at the quantum level. Some models suggest that monopoles could be a form of dark matter, providing a clue to the nature of this mysterious substance. If monopoles are found to interact with other forms of matter in a way that could explain the properties of dark matter, it could be one of the most significant discoveries in the history of physics. One of the key features of quantum mechanics is its probabilistic nature. Particles do not have definite positions or velocities until they are measured, and the act of measurement itself affects the system. This uncertainty is a fundamental aspect of quantum theory and is captured by Heisenberg's uncertainty principle. The discovery of magnetic monopoles could provide a new way to understand this uncertainty and might offer insights into how quantum systems evolve over time. It is possible that the introduction of monopoles could lead to new forms of uncertainty or new ways of measuring quantum states, providing further clarity on the role of measurement in quantum systems. The potential implications of monopoles for quantum mechanics are far-reaching and could reshape the way we understand the behavior of particles at the smallest scales. The discovery of a monopole would not only confirm a long-standing theoretical prediction, but would also provide a new tool for exploring the mysteries of quantum physics. It could lead to advances in quantum computing, quantum communication, and material science, and it could open up new areas of research into the unification of the fundamental forces of nature. The connection between monopoles and quantum physics is still speculative, but the possibility of their existence has already inspired new theories and experiments that could one day reshape the landscape of quantum mechanics. Whether or not the monopole is ever detected, its potential to deepen our understanding of the quantum world makes it one of the most exciting and promising frontiers in modern physics. The potential discovery of the magnetic monopole holds deep implications for the standard model of particle physics, the framework that describes the fundamental particles and forces of the universe. The standard model has been remarkably successful in explaining a wide range of phenomena, from the interactions of quarks and leptons to the behavior of electromagnetic, weak, and strong forces. It provides a comprehensive and well-tested description of the building blocks of matter and the forces that govern their interactions. However, despite its success, the standard model is not complete. There are still significant gaps in our understanding, and one of the most glaring issues is the inability of the standard model to account for all the fundamental forces, particularly gravity, and the mysterious nature of dark matter. The introduction of the magnetic monopole could be the key to unlocking some of these unanswered questions, potentially leading to a revision, or even an extension of the standard model. One of the most immediate implications of discovering a magnetic monopole would be the need to revise the way we understand electromagnetism within the standard model. Currently, Maxwell's equations, which describe the behavior of electric and magnetic fields, are based on the assumption that magnetic fields always come in pairs, north and south poles. This is a deeply ingrained concept in electromagnetism, and the entire framework of the standard model is built upon this principle. If magnetic monopoles exist, it would challenge this assumption and require a modification of the equations that describe electromagnetism. A monopole would add an asymmetry to the electromagnetic field, creating a magnetic charge that behaves in a fundamentally different way from the electric charge that we are familiar with. This would have profound implications for the structure of electromagnetism, as it would require a rethinking of how electric and magnetic fields interact and how they are described mathematically. The standard model is also built around the idea that particles interact through the exchange of force-carrying particles called gauge bosons. For example, the electromagnetic force is mediated by the photon, while the strong nuclear force is mediated by gluons. These gauge bosons are the carriers of the fundamental forces, and their properties are well understood in the context of the standard model. The introduction of the magnetic monopole would add a new dimension to this framework, as it would imply the existence of a new type of gauge boson, a hypothetical particle that would mediate the interaction between monopoles and other particles. This new gauge boson, which could be a massive particle, would need to be incorporated into the standard model, potentially leading to a more unified description of the fundamental forces. The existence of monopoles could therefore suggest that the standard model, while successful in many areas, is incomplete and in need of revision to account for this new class of particles. Another significant implication of the magnetic monopole for the standard model involves the relationship between electric and magnetic charges. The existence of monopoles would introduce a symmetry between electric and magnetic charges, a concept that has never been realized in nature. In the current model, electric charges are positive or negative, and they interact with electric fields. Magnetic charges, on the other hand, only appear in dipoles, pairs of north and south poles, with no isolated magnetic charge. The existence of monopoles would bridge this gap, providing a magnetic counterpart to electric charge. This symmetry could lead to a deeper understanding of the relationships between the fundamental forces, potentially offering a new perspective on how electromagnetism works and how it might be unified with other forces such as the weak and strong nuclear forces. This symmetry could be a stepping stone toward a grand, unified theory of the forces of nature, which is one of the holy grails of modern physics. The discovery of monopoles could also help to resolve some of the unresolved questions within the standard model itself. For example, the quantization of electric charge, the idea that the charge of elementary particles is always an integer multiple of a fundamental unit, has been a key feature of the standard model. However, the exact mechanism that forces electric charge to be quantized has never been fully understood. Dirac's original prediction of the magnetic monopole suggested that the presence of monopoles could explain this quantization. If monopoles exist, they could provide the missing link between the electric and magnetic forces, offering a way to explain why electric charge is quantized in discrete amounts. The discovery of the monopole would therefore provide a potential solution to this long-standing puzzle, and could lead to a deeper understanding of the nature of charge and its connection to the electromagnetic field. Additionally, the standard model has always struggled to incorporate gravity, the fourth fundamental force. While the electromagnetic, weak and strong forces are well described by the standard model, gravity has remained outside its purview. The theory of general relativity, which describes gravity, is based on a very different framework and does not fit neatly with the other three forces. If monopoles are real, their discovery could provide a bridge between quantum mechanics and general relativity, two theories that currently do not reconcile with each other. Some theoretical models suggest that monopoles could play a role in a more unified theory that combines gravity with the other three forces. This could lead to a deeper understanding of how gravity fits into the standard model and how it might be incorporated into a theory of everything, a unified framework that explains all of the forces of nature in a single theory. In this way, the magnetic monopole could help resolve one of the most profound challenges in modern physics, the unification of general relativity and quantum mechanics. The implications of the magnetic monopole for dark matter are equally significant. Dark matter, the invisible substance that makes up a substantial portion of the universe's mass, has been one of the most persistent mysteries in cosmology. While we know that dark matter exists due to its gravitational effects on visible matter, we have yet to detect it directly. Some theorists have suggested that magnetic monopoles could be linked to dark matter. If monopoles are real, they could form part of the dark matter that fills the universe, providing a potential explanation for this enigmatic substance. The discovery of monopoles would therefore not only revolutionize our understanding of the standard model, but could also provide a crucial piece of the puzzle in understanding the nature of dark matter and its role in the formation of galaxies and other cosmic structures. The discovery of the magnetic monopole would mark a fundamental shift in how we view the universe and the forces that govern it. It would challenge the core principles of the standard model and force us to reconsider the very nature of electromagnetism, charge, and the interactions between fundamental particles. The standard model has been incredibly successful, but it is not complete. The magnetic monopole could be the missing piece that opens the door to a more unified, more complete theory of the universe. one that integrates electromagnetism with the other fundamental forces and incorporates gravity in a way that the standard model cannot. Whether or not monopoles are eventually discovered, their theoretical predictions have already pushed the boundaries of physics, leading to new questions, new ideas, and the possibility of a new era in scientific discovery. The future of the standard model, and indeed of physics itself, may depend on whether monopoles are found, and their discovery could lead to one of the most profound revolutions in our understanding of the universe. The search for dark matter is one of the most exciting and elusive quests in modern science, and its connection to the magnetic monopole adds an intriguing layer to an already complex mystery. Dark matter, which is thought to make up approximately 27% of the universe's mass, cannot be observed directly through conventional means, such as visible light or electromagnetic radiation. Instead, scientists infer its presence from its gravitational effects on visible matter. Galaxies, for example, rotate in a way that suggests they contain far more mass than we can see, and the way galaxies cluster together also points to the existence of some unseen, mysterious substance. Yet, despite decades of research and sophisticated observational techniques, the nature of dark matter remains one of the greatest unsolved problems in physics. Could the magnetic monopole be the key to understanding dark matter? The magnetic monopole has long been speculated to have a connection to dark matter, though this idea is still theoretical. The search for dark matter has traditionally focused on particles like weakly interacting massive particles, WIMPs, axions and sterile neutrinos, candidates that interact very weakly with ordinary matter and thus cannot be easily detected. However, some models suggest that magnetic monopoles could also be a component of dark matter, adding a new dimension to the search for this elusive substance. If monopoles are indeed part of dark matter, their discovery could provide a major breakthrough in our understanding of the universe's composition. Dark matter is invisible in the sense that it does not emit, absorb or reflect light, making it undetectable by traditional electromagnetic means. Theoretical candidates like WIMPs are thought to interact with ordinary matter via the weak nuclear force, a force that only affects particles on subatomic scales. Similarly, magnetic monopoles are predicted to interact with the electromagnetic force, but in a very different way compared to typical particles like electrons or protons. If monopoles exist, they would behave as magnetic charges, interacting with magnetic fields rather than electric fields. While they are not expected to interact strongly with ordinary matter, their interactions with dark matter and other particles could still leave detectable signatures, offering a new path to explore in the search for dark matter. One possible connection between monopoles and dark matter stems from the idea that the early universe may have produced both monopoles and dark matter in the extreme conditions shortly after the Big Bang. In the first moments after the universe began, temperatures were so high that all four fundamental forces, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, were unified into a single force. As the universe cooled, these forces separated, and monopoles might have emerged as relics from this phase of unification. Some theories suggest that these monopoles could have remained stable and invisible, contributing to the overall mass of dark matter. The concept of monopoles as a form of dark matter would also fit well with some of the existing theories of how dark matter interacts with ordinary matter. For example, many models of dark matter involve the idea that dark matter particles could clump together in large halos around galaxies, affecting their rotation and behaviour. If monopoles are present in these halos, they could contribute to the gravitational effects attributed to dark matter, adding a new layer of complexity to the dark matter picture. Their potential interaction with magnetic fields could also lead to phenomena that have not yet been observed, providing new avenues of research for astrophysicists and cosmologists trying to understand the dark matter that pervades the universe. However, while the idea of monopoles as dark matter candidates is intriguing, it remains highly speculative. Theoretical models suggest that monopoles, if they exist, would be extremely rare, and their interactions with ordinary matter would be weak enough that they might be very difficult to detect. This makes it challenging to design experiments that could conclusively prove their existence or rule them out as dark matter candidates. In practice, monopoles would be hard to distinguish from other forms of dark matter, particularly in the context of the weakly interacting massive particle, WIMP, and axion models, which also predict particles that interact weakly with matter. Nonetheless, the magnetic monopole's potential to interact with magnetic fields gives it a unique property that could make it detectable through methods that are not applicable to other dark matter candidates. The search for dark matter has driven the development of increasingly sophisticated detection techniques, some of which might be able to spot monopoles if they are part of dark matter. One approach is to look for signals of monopoles interacting with magnetic fields in astrophysical environments. If monopoles are present in galactic halos, they could affect the behavior of cosmic magnetic fields, leading to observable effects in the cosmic microwave background, CMB radiation. The CMB, which is the afterglow of the Big Bang, carries a wealth of information about the early universe. Tiny distortions in the CMB could be caused by the presence of monopoles interacting with cosmic magnetic fields, providing indirect evidence for their existence. Another approach could involve direct detection experiments, which are designed to look for evidence of dark matter particles interacting with detectors on Earth. These experiments often look for rare, weak interactions between dark matter particles and atoms in highly sensitive detectors, such as those used in the search for WIMPs. If monopoles are part of dark matter, it might be possible to detect them by observing their unique interactions with the detector material. Because monopoles would interact differently with magnetic fields, they might leave a distinct signature that could help distinguish them from other dark matter candidates. This could involve looking for unusual magnetic field patterns or energy deposition patterns in detectors that are sensitive to the presence of magnetic charges. If monopoles are indeed discovered and found to be a component of dark matter, it would revolutionize our understanding of both dark matter and the fundamental forces of nature. It would provide a direct link between the behavior of dark matter and the electromagnetic force, which is not currently accounted for in standard dark matter models. Moreover, it could offer new insights into the early universe and the processes that took place during the Big Bang. The discovery of monopoles would also raise new questions about the nature of dark matter and its role in the formation and evolution of the universe. It could help scientists understand how dark matter interacts with ordinary matter and how it has influenced the structure of the cosmos. While we are still far from confirming that monopoles are part of dark matter, the possibility that they are is an exciting prospect. The search for dark matter and the search for magnetic monopoles are intertwined in a way that could lead to groundbreaking discoveries in the future. Whether or not monopoles turn out to be the missing piece of the dark matter puzzle, their potential existence represents a key to understanding the mysteries of the universe, from the behavior of particles at the smallest scales to the formation of galaxies and the nature of the cosmos itself. The connection between monopoles and dark matter is a reminder of how much we still have to learn about the universe. Dark matter is one of the most profound mysteries of modern physics, and the possibility that monopoles could be the answer to this mystery offers an exciting new avenue of research. The search for these particles is still ongoing, with scientists around the world developing new techniques and experiments to detect dark matter and monopoles. As we continue to explore the unknown, the discovery of monopoles would not just solve one puzzle, it could open up a whole new chapter in our understanding of the universe's most fundamental questions. The search for the magnetic monopole has already had a profound impact on the field of physics, driving theoretical models, experimental techniques, and technological innovations. For nearly a century, this elusive particle has captured the imagination of scientists, representing an ultimate test of the boundaries of our understanding of the universe. As the possibility of its discovery moves closer to reality, many physicists are beginning to ask a more profound question. Are we on the verge of a new physics revolution? If the magnetic monopole is found, it could bring about far-reaching changes in the way we view the fundamental forces of nature, the structure of the universe, and the laws that govern all matter. The implications for both theoretical and experimental physics are immense, and the discovery could mark a new chapter in the story of scientific discovery. One of the first revolutions that a discovery of the magnetic monopole could bring about is a rethinking of the very foundation of electromagnetism. For centuries, the understanding of magnetism has been based on the idea that magnetic fields always come in pairs, north and south poles never existing independently. Maxwell's equations, which form the core of classical electromagnetism, are built on this assumption. These equations describe how electric and magnetic fields interact and how they give rise to the electromagnetic force. The concept of the monopole, a magnetic charge that exists independently, would challenge this principle, forcing a revision of Maxwell's equations and how we understand the interactions between electric and magnetic fields. Such a change would not be a small modification, but a profound shift in our understanding of one of the most fundamental forces in nature. The electromagnetic field could no longer be described as a simple dipole. It would require a new framework, one that could potentially unify electricity and magnetism in a more profound way. This shift in electromagnetism could ripple through other areas of physics. If magnetic monopoles exist, they would introduce a symmetry between electric and magnetic charges, something that has never been fully realized in nature. This symmetry could lead to new insights into the relationship between these two forces, potentially providing a path toward unifying the electromagnetic force with the other fundamental forces. In fact, the existence of monopoles could represent the first tangible step toward a unified theory of all fundamental interactions, one that connects electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. While the standard model of particle physics successfully describes 3 of the 4 forces, gravity remains absent from its framework. The discovery of monopoles could shed light on how all the forces might be related, providing a foundation for the long-sought theory of everything, TOE, that could bring together quantum mechanics and general relativity. Beyond the direct implications for electromagnetism, the detection of a magnetic monopole would spark a revolution in our approach to quantum mechanics. Quantum theory is already a vast and complex field, and its understanding continues to evolve. The existence of monopoles could offer new insights into the strange behavior of particles at the quantum level. In particular, monopoles might play a role in some of the most perplexing phenomena in quantum mechanics, such as quantum entanglement and quantum tunneling. These phenomena, which defy classical intuition, are central to the functioning of quantum computers and other cutting-edge technologies. If monopoles can interact with quantum states in specific ways, they could potentially be harnessed to improve our ability to control and manipulate quantum systems, leading to breakthroughs in computing, encryption, and materials science. Furthermore, the search for magnetic monopoles has already driven advancements in experimental techniques and technology. Particle accelerators like the Large Hadron Collider, LHC, have pushed the limits of what is possible in terms of energy and precision, allowing scientists to probe deeper into the fundamental nature of matter. These advancements in experimental capabilities are not limited to the search for monopoles, but have broader implications for particle physics as a whole. The tools and methods developed in the search for monopoles have already contributed to other groundbreaking discoveries, such as the detection of the Higgs boson, and they will continue to shape the future of high-energy physics for years to come. If monopoles are indeed discovered, it will mark a turning point in the field of particle physics, not only because of the direct impact on our understanding of the forces of nature, but also because it would open up entirely new lines of inquiry. For example, as we learn more about how monopoles behave, we may uncover new types of particles or fields that we have yet to imagine. The detection of monopoles could prompt the search for other exotic particles, leading to a broader exploration of the universe at the smallest scales. We might begin to understand new interactions between fundamental particles, the nature of dark matter, and the ways in which the early universe operated in the first moments after the Big Bang. This could spark an entirely new generation of theoretical models, each offering a different perspective on the underlying fabric of reality. In addition to its impact on theoretical physics, the discovery of the magnetic monopole could lead to practical revolutions in technology. If monopoles can be produced or controlled, they could be used in a wide range of applications, from advanced materials and energy storage systems to quantum computers and high-performance sensors. The unique properties of monopoles, particularly their interactions with magnetic fields, could give rise to new technologies that exploit these properties in novel ways. For instance, monopoles might allow for the development of materials with extraordinary magnetic properties, leading to more efficient energy generation and storage solutions. In the realm of quantum computing, monopoles could help stabilize qubits, the fundamental units of quantum information, making it possible to build larger, more reliable quantum systems. These technologies could have far-reaching effects, potentially revolutionizing industries ranging from computing and telecommunications to energy and manufacturing. Beyond these practical applications, the discovery of monopoles would have profound philosophical implications. For centuries, physics has been driven by the belief that the universe operates according to a set of simple, elegant laws that can be uncovered through observation and experimentation. The search for monopoles represents a key part of this ongoing pursuit of knowledge. Discovering such a fundamental particle would not only answer a long-standing question in physics, but would also open the door to deeper questions about the nature of reality itself. What is the relationship between magnetism and electricity? How do the forces of nature operate at the most fundamental level? What other mysteries lie hidden, waiting to be uncovered? These questions are what drive scientists to explore the unknown, and the discovery of monopoles would be a momentous step toward answering them. As the search for the magnetic monopole continues, scientists around the world are becoming increasingly optimistic that a breakthrough could be on the horizon. The tools and techniques necessary for detecting monopoles are improving, and the theoretical frameworks for understanding them are becoming more sophisticated. The discovery of the monopole would not just be a scientific milestone, it would mark the beginning of a new era in physics, one where new ideas, new technologies, and new perspectives come to the forefront. The implications for our understanding of the universe, the forces that govern it, and the technologies that shape our future are vast. As we stand on the edge of this potential discovery, it's clear that the search for the magnetic monopole is about more than just finding a new particle. It's about revolutionizing the way we think about the universe itself, opening up new frontiers of knowledge and exploration. Are we on the verge of a new physics revolution? If the magnetic monopole is found, the answer will be a resounding yes. The discovery of this particle would transform our understanding of the universe and usher in a new era of scientific inquiry, one that could change the very fabric of reality itself. Whether or not this discovery happens in the near future, the pursuit of the monopole will continue to inspire generations of physicists to push the boundaries of what is known and seek answers to some of the deepest questions in science. The revolution, whether it happens today or in the years to come, will be driven by the unyielding curiosity that fuels the search for understanding in the infinite complexity of the cosmos. As the search for magnetic monopoles progresses, the spotlight increasingly turns to CERN, one of the world's most prominent research facilities for particle physics. With its vast array of particle accelerators and cutting-edge detection technologies, CERN has become the focal point of the hunt for some of the most elusive particles in nature, including the magnetic monopole. Over the years, CERN's experiments have reshaped our understanding of the fundamental forces of the universe, culminating in groundbreaking discoveries like the Higgs boson. Now, with the magnetic monopole potentially within reach, CERN is once again poised to push the boundaries of physics and possibly unlock a new chapter in our understanding of the cosmos. The Large Hadron Collider, LHC, at CERN, the world's most powerful particle accelerator, is at the heart of this search. The LHC accelerates protons to nearly the speed of light before smashing them together in high-energy collisions. These collisions recreate conditions similar to those that existed just moments after the Big Bang, where all the fundamental forces of nature were unified. It is in these extreme conditions that new, exotic particles, such as the magnetic monopole, could potentially be produced. However, detecting a monopole is no easy feat. As a highly rare and elusive particle, it requires highly sensitive detectors, a deep understanding of its potential interactions with other particles, and a great deal of experimental ingenuity. One of the next major steps for CERN in the search for magnetic monopoles is refining its detection capabilities. While the LHC and other particle accelerators have already been instrumental in exploring the fundamental particles that make up the standard model, discovering the monopole will require more than just powerful collisions. It will involve using highly specialized detectors that can differentiate monopoles from the myriad of other particles created in these collisions. These detectors will need to identify unique magnetic signatures and track the monopole's interactions with electromagnetic fields, a behavior that is fundamentally different from the interactions of more familiar particles like protons and electrons. As the technology used in these detectors advances, so too does the ability to observe and isolate the subtle effects that might indicate the presence of a monopole. At the same time, CERN's ongoing experiments are focused on expanding the theoretical models that predict the existence of monopoles. These models suggest that monopoles could be produced under specific conditions that might be recreated more readily as CERN continues to push the energy limits of its particle collisions. Theoretical advancements in the understanding of monopoles are closely tied to the experimental work being done at CERN, as researchers explore new ways to create and detect these particles. By fine-tuning the experimental conditions and improving the accuracy of simulations, CERN scientists are refining their predictions and strategies for detecting monopoles in future runs of the LHC. This includes developing more detailed models of how monopoles would behave in the intense electromagnetic fields generated during particle collisions and predicting the specific signatures that would result from their interactions. While the LHC is the most powerful tool available to CERN for exploring high-energy physics, other experiments at CERN are also contributing to the search for magnetic monopoles. Experiments that focus on cosmic rays, for example, are exploring the possibility that monopoles could be found in the high-energy particles that constantly bombard Earth from space. These cosmic rays could potentially provide another avenue for detecting monopoles, especially if they interact with the Earth's magnetic field in unique ways. By combining data from particle accelerators with observations of cosmic particles, CERN can take a more comprehensive approach to searching for monopoles in a variety of environments. Beyond the direct search for monopoles, CERN's work is also closely tied to the broader goal of understanding the fundamental forces of nature. In many ways, the search for monopoles is part of a larger effort to answer some of the most profound questions in physics. How do the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, relate to each other? How can they be unified into a single framework? The magnetic monopole, with its potential to link electric and magnetic charges in a new and profound way, could offer insights into the unification of forces, a goal that has been pursued for decades. If monopoles exist, they could provide a bridge between electromagnetism and the other forces, contributing to a deeper understanding of how these forces are connected and how they might have been unified in the early moments of the universe. As CERN moves forward in its experiments, the role of international collaboration cannot be overstated. The search for monopoles is not just a task for CERN alone. Scientists and researchers around the world are contributing to this global effort. Collaborations between universities, research institutes, and other scientific organizations are bringing together the best minds in theoretical and experimental physics to tackle one of the most fundamental questions in science. The shared knowledge and resources of these international teams will be crucial in pushing the boundaries of what is possible, advancing both the theoretical models of monopoles and the experimental techniques needed to detect them. By fostering this spirit of global cooperation, CERN ensures that the search for monopoles, and the deeper insights it might yield will continue to evolve and expand. Looking ahead, one of the most exciting prospects for CERN is the possibility that the discovery of the magnetic monopole could be just the beginning of a new era in physics. If monopoles are found, they would not only provide answers to long-standing questions about electromagnetism, but also open up new avenues for exploration. Scientists would be tasked with investigating the properties of monopoles in greater detail, testing their interactions with other particles, and uncovering the broader implications for the standard model and beyond. For example, if monopoles can be controlled or manipulated, they could lead to the development of new technologies such as advanced quantum computers or new materials with extraordinary magnetic properties. But the journey does not end with the discovery of monopoles. If monopoles are confirmed, they could be the first of many new particles and phenomena to be discovered in the unexplored realms of physics. The discovery of the monopole could unlock the potential for finding other exotic particles, expanding our understanding of the universe at the most fundamental level. For example, monopoles might provide clues to the nature of dark matter, a mysterious substance that makes up a large portion of the universe's mass, but has yet to be detected directly. If monopoles are found to interact with dark matter, it could revolutionize our understanding of the cosmos and offer new pathways to exploring the fundamental structure of the universe. In conclusion, the search for magnetic monopoles at CERN is far from over, but the progress made so far suggests that the possibility of their discovery is within reach. The next few years could be pivotal in determining whether monopoles are a real and integral part of the universe's fundamental makeup. For CERN, the pursuit of the monopole is more than just an experiment. It is a journey that could redefine our understanding of the universe itself. As new experiments are run, new theoretical models are developed, and new technologies are deployed, the search for monopoles will continue to evolve, potentially leading to one of the most transformative breakthroughs in the history of physics. The future of particle physics is bright, and the discoveries that lie ahead may forever change our view of the forces that shape the universe. As we bring this exploration of the magnetic monopole to a close, it's clear that this elusive particle has captivated the imagination of scientists for nearly a century, and its potential discovery stands to reshape the very foundations of physics. What began as a theoretical idea in the early 20th century has evolved into one of the most exciting and challenging quests in modern science. The possibility of uncovering the magnetic monopole is more than just a pursuit of a new particle. It represents a deeper, more profound journey toward understanding the universe at its most fundamental level. Over the course of this exploration, we've looked at the significance of the magnetic monopole from various angles, its role in theoretical physics, its implications for electromagnetism, and its potential connection to the mysteries of quantum mechanics and dark matter. We've examined how its discovery could force us to rethink everything from the symmetry of the electromagnetic field to the very nature of the forces that govern the universe. A monopole, if found, would be a key to unlocking a new realm of understanding, a piece of the puzzle that might help to unify the forces of nature and offer insight into phenomena like dark matter, quantum entanglement, and the unification of gravity with the other fundamental forces. For CERN, the search for the magnetic monopole represents a major focus, with its cutting-edge technology, such as the Large Hadron Collider, offering a unique environment to probe the deepest questions in particle physics. The challenges in detecting a monopole, its rarity, its unique interactions with fields, and its possible role in dark matter, have made the search a complex and difficult one. Yet, the progress made thus far is encouraging, and the potential for a breakthrough remains very real. Theoretical predictions combined with new experimental techniques and increasingly sensitive detectors have positioned CERN at the forefront of the quest to find this elusive particle. But the search for the monopole is not just about the discovery of a single particle, it is part of a broader scientific journey that stretches across generations. Whether or not monopoles are ultimately found, the pursuit has already yielded invaluable insights into the universe's workings. It has driven new discoveries, challenged old assumptions, and pushed the limits of experimental technology. More than that, it serves as a testament to the curiosity and persistence of the scientific community, a reminder that even the most improbable ideas, when tested and explored, can lead to transformative discoveries. As we reflect on the significance of the magnetic monopole and its place in the ongoing pursuit of scientific knowledge, it becomes clear that this search is about far more than just uncovering new particles. It is about expanding the boundaries of human understanding, pushing beyond the known and into the unknown. The potential discovery of the monopole would mark the beginning of a new era in physics, one where new ideas and new possibilities emerge, reshaping our view of the universe and the laws that govern it. The journey is far from over, and the answers we seek may be just beyond the horizon. For now, the search for the magnetic monopole continues, driven by a desire to uncover the mysteries of the cosmos and to deepen our understanding of the fundamental forces that shape everything we know. The pursuit of this elusive particle is a reminder that in science, the impossible is always worth exploring, and even the most difficult questions can one day lead to answers that change everything. Whether or not we find the monopole in the near future, the journey itself is an essential part of the ongoing quest for knowledge, one that will continue to inspire generations of scientists and thinkers long into the future. And so, as we reflect on this fascinating quest, we are reminded that the search for the unknown is what propels us forward. The magnetic monopole may be just one of many mysteries that await us, but its discovery would undoubtedly be a landmark achievement in the history of science, ushering in a new era of understanding that could change the way we see the universe forever.